There's something profoundly humbling about looking up at the night sky, knowing that every twinkling light is a star, each with its own story, its own life cycle, governed by laws we thought we understood. But what if I told you that some of those stars are breaking all the rules, defying every textbook, every model, every assumption astronomers have ever made about how the universe works? These aren't just outliers, they're cosmic rebels, anomalies so bizarre they're forcing us to tear up the old playbook and start from scratch. Today, we're diving into 23 of the most mind-bending galactic mysteries ever discovered, celestial phenomena that challenge everything we know about stellar evolution. Picture a star hurtling through space at millions of miles per hour, faster than anything should be able to move, or a gaping void in the cosmos where stars simply refuse to form, as if the universe itself forgot to fill in the blanks. These aren't science fiction, they're real, documented enigmas that have left even the most seasoned astrophysicists scratching their heads. And the deeper we look, the more we realize how little we truly understand. Every time we think we've got it all figured out, the universe throws us another curveball, reminding us that the cosmos is far stranger, far more unpredictable than we ever imagined. This journey isn't just about cataloging oddities, it's about rewriting the story of the stars themselves. Each of these anomalies is a clue, a piece of a puzzle that could unlock entirely new chapters in astrophysics. Some might reveal hidden forces at work, while others could point to gaps in our fundamental understanding of gravity, light, or even the fabric of space-time. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe is speaking, and what it's saying will leave you in awe. There's something almost poetic about stars that refuse to be tied down, cosmic nomads racing through the void at speeds so extreme, they leave their home galaxies behind. These are hypervelocity stars, and they're not just breaking the speed limit, they're tearing up the rulebook on how gravity should behave. Imagine a star born in the crowded heart of a galaxy, suddenly flung outward like a slingshot projectile, moving faster than 500 kilometers per second. That's not just unusual, it's physically improbable under our current understanding of stellar motion. So how do these runaway stars defy gravity's grip? The leading theory points to supermassive black holes lurking at galactic centers. When a binary star system drifts too close, one star gets captured while the other is violently ejected, accelerated to unimaginable speeds. But here's where it gets even stranger. Some hypervelocity stars appear to originate from regions without massive black holes, leaving astronomers scrambling for alternative explanations. Could supernova explosions be kicking them into the void? Or is there something more exotic at play, like interactions with elusive dark matter? What makes these stellar speedsters so revolutionary isn't just their velocity, it's what they reveal about the hidden forces sculpting galaxies. Every hypervelocity star we track is a breadcrumb trail, hinting at violent events we can't directly observe. They force us to reconsider how energy is distributed across the cosmos and whether our models of galactic dynamics are missing critical pieces. And yet, for all their mystery, they're just the opening act in a far larger cosmic drama. Because if stars can defy gravity this spectacularly, what else might be out there, waiting to upend everything we think we know? If hypervelocity stars challenge our understanding of motion, then the next anomaly shatters something even more fundamental: time itself. Meet Methuselah, the star that shouldn't exist. Clocking in at an estimated 14.5 billion years old, this ancient relic appears older than the universe's calculated age of 13.8 billion years. It's like finding a grandfather clock that ticks backward, mocking the very laws of cosmology. How can a star predate the cosmos that birthed it? The answer lies in a tug of war between two possibilities. Either our methods for dating stars are fatally flawed, or the early universe hosted conditions so alien they birthed stars in ways we've never imagined. Take stellar age dating, a process astronomers once considered straightforward. By analyzing a star's composition, particularly its lack of heavy elements, we can estimate its birth era. The logic is simple: the older the star, the purer its hydrogen and helium, since heavier elements hadn't yet been forged in stellar furnaces. But Methuselah throws a wrench into this tidy system. Its chemical makeup suggests extreme antiquity, yet its position and motion align with younger stars. Could interstellar theft swiping material from neighboring stars have contaminated its pristine signature? Or does its strange orbit hint it was stolen from a dwarf galaxy, where star formation might have begun earlier? Then there's the nuclear option, literally. Some theorists argue we've underestimated how quickly early stars burned their fuel. In the universe's infancy, densities were higher, and nuclear reactions might have unfolded differently, making stars appear older than they truly are. Others propose even wilder ideas, like pockets of the cosmos where time flowed slower due to intense gravitational fields, effectively giving certain stars a head start. But perhaps the most humbling takeaway is this: Methuselah isn't alone. Several other stars flirt with similarly impossible ages, suggesting our cosmic timeline might need more than a tweak, it might need a rewrite. And just when you think the universe couldn't get any weirder, it pulls another vanishing act. Some stars don't just age mysteriously, they disappear entirely. One moment they're shining steadily in telescope data, the next they're gone, leaving no trace of a supernova or black hole. These aren't dimming stars or camera glitches. Over a dozen have vanished in recent decades without explanation. Could they have collapsed directly into black holes, skipping the explosive finale? Or is something even stranger at work, like exotic physics warping light so completely it erases them from view? Whatever the cause, each missing star is a reminder. The cosmos holds cards it hasn't shown us yet. One of the most unsettling mysteries in modern astronomy isn't about what we see in the cosmos, it's about what vanishes before our eyes. Picture this: astronomers point their telescopes at a familiar patch of sky, a star catalogued for decades shining steadily, only to return later and find nothing. No explosion, no fading ember, just an empty space where a star once burned. Over 100 of these disappearing acts have been documented, and each one chips away at our understanding of how stars live and die. The leading theory: some stars might be taking the ultimate cosmic shortcut, collapsing directly into black holes without the fireworks of a supernova. It's like watching a magician's trick where the assistant steps into a box and never comes out. No smoke or mirrors, just pure vanishing. Normally, when massive stars die, they go out with a bang, scattering their guts across space in a brilliant explosion visible for light years. But if a star's core is heavy enough, it might bypass the spectacle entirely, imploding so completely that not even light escapes. The problem: we've never caught one in the act. These failed supernovae should leave behind telltale shockwaves or neutrino bursts, yet detectors remain eerily silent. Then there's the wild-card explanation, one that straddles the line between astrophysics and science fiction. Could these missing stars be evidence of something artificial? The idea of Dyson spheres, hypothetical megastructures built by advanced civilizations to harness a star's energy, has tantalized theorists for decades. If a civilization were to dismantle a star piece by piece, or enclose it completely, the result would match what we're observing: a star that winks out of existence without a trace. While the odds are slim, the sheer scale of the universe means we can't dismiss the possibility outright. After all, nature rarely leaves gaps this glaring without a reason. What makes these disappearances so unnerving is their randomness. Some stars vanish overnight, others fade gradually over years. A few even flicker erratically before disappearing, as if the cosmos itself is toying with us. And with every new observation, the mystery deepens. Projects like the vanishing and appearing sources during a century of observations, Vasco are scanning old photographic plates, comparing them to modern data, and uncovering more gaps in our stellar records. Each missing star is a breadcrumb pointing toward phenomena we've yet to name or understand. If stars can vanish without a trace, what does that say about the stability of the cosmos itself? Are there entire populations of stars slipping through the cracks, dying quietly in the dark? Or are we witnessing the fingerprints of forces, natural or otherwise, that operate beyond the boundaries of known physics? One thing's certain, the universe is full of stagehands, and they're far better at hiding their work than we ever imagined. Now, imagine a star that doesn't just disappear, but flickers unpredictably like a candle caught in a draft. These aren't the steady pulses of variable stars we've come to expect. They're erratic, almost chaotic, as if something vast and unseen is passing between the star and us, casting shadows we can't explain. Some stars don't just shine, they stutter. Imagine a cosmic light bulb flickering unpredictably, dimming and flaring with no discernible rhythm, as if the star itself is gasping for breath. These aren't your typical variable stars which pulse with clockwork regularity. These are the flickering giants, massive, turbulent beasts whose light dances erratically, defying every model of stellar behavior we've built. And the strangest part, we still don't know what's pulling their strings. One clue lies in their atmospheres. Normally, a star's outer layers behave like a well-orchestrated symphony, with energy rising and falling in predictable waves. But these flickering giants seem to be playing a different tune entirely. Some astronomers think uneven dust clouds might be to blame, swirling, asymmetric veils that intermittently block their light like cosmic shutters. The problem, dust alone can't explain the sheer violence of these brightness swings. We're talking drops of up to 40% in luminosity, far beyond what simple obscuration should cause. Then there's the internal instability theory. Picture a star's core as a bubbling cauldron of nuclear reactions, where energy normally flows outward in a steady current. But in these stars, that flow might be hitting turbulence like water crashing through a broken pipe. Convection cells could be collapsing chaotically, or magnetic fields might be twisting the star's interior into knots, creating bottlenecks where energy gets trapped and then explosively released. The catch, we've never observed this level of instability in stars of this size. If confirmed, it would mean our understanding of stellar energy transport is missing entire chapters. But the real shocker comes when we look at their magnetic fields. Some of these flickering giants exhibit magnetism so intense, it warps the very fabric of their plasma. Normally, a star's magnetic field is an orderly thing, shaping solar flares and sunspots. But in these stars, the fields are tangled and frenetic, as if the star is caught in a cosmic tug of war with itself. Could these magnetic monstrosities be the key to the flickering? It's possible, except that, according to current models, stars this massive shouldn't be able to sustain fields this powerful without tearing themselves apart. Yet here they are, glowing defiantly, daring us to explain them. What makes these flickering giants so revolutionary isn't just their odd behavior, it's what they reveal about the limits of our knowledge. Every erratic pulse is a message, a clue that stellar evolution might be far more dynamic and violent than we ever imagined. And as we peel back the layers of this mystery, we're led to an even more perplexing question. What happens when a star's magnetic field doesn't just flicker, but becomes something truly impossible? If flickering stars make us question stellar stability, then magnetars force us to rewrite the laws of physics entirely. These neutron stars aren't just dense, they're cosmic electromagnets with fields so powerful they could strip the electrons from atoms halfway across a galaxy. Picture a magnetic field 1,000 trillion times stronger than Earth's, capable of warping the very shape of matter itself. According to our models, such intensity should be impossible. Yet magnetars exist, pulsing with violent energy, and their very presence cracks open glaring holes in our understanding of extreme matter. How do these ultramagnetic monsters form? The leading theory involves stellar mergers, two neutron stars colliding in a cataclysm so violent, it twists their combined magnetic fields into a knotted frenzy. But there's a problem. Even the most violent mergers shouldn't produce fields this strong. Some researchers speculate quantum effects might be at play, with subatomic particles aligning in ways we've never observed in laboratories. Others propose these magnetars are born from supernovas so rare, we've yet to witness one directly explosions that leave behind cores with magnetism dialed up to cosmic extremes. Then there's the real kicker. Magnetars don't just sit quietly, they erupt. Without warning, these stars release bursts of gamma rays and X-rays so intense, they can ionize Earth's upper atmosphere from 50,000 light-years away. In 2004, a magnetar flare from the other side of our galaxy temporarily blinded satellites and altered radio wave propagation across the planet. It's as if these stars are shouting their defiance across the cosmos, reminding us how little we grasp about the forces that shape them. What makes magnetars truly revolutionary isn't just their strength, it's what they imply about the fabric of reality. Under such crushing magnetic fields, protons and neutrons might deform into exotic shapes, or even dissolve into a soup of quarks. Some theories suggest magnetars could be portals to states of matter that only existed microseconds after the Big Bang. Yet for all their fury, they're also eerily precise. Their spin rates slow predictably, as if the universe is using them as cosmic clocks, ones ticking to rhythms we don't yet comprehend. And just when you think magnetism can't get any stranger, the cosmos reveals stars that burn fuel we never thought possible. Not hydrogen, not helium, but something far more unexpected, rewriting the rules of stellar chemistry right before our eyes. Stars are supposed to follow the rules, burning fuel in predictable ways, fusing elements in orderly layers like a cosmic onion. But deep in the galaxy's corners, some rebels are playing by their own nuclear playbook. These aren't just oddballs, they're celestial alchemists performing fusion reactions that, by all known physics, should be impossible. Take the case of carbon stars, aging giants that somehow produce vast amounts of carbon in their cores despite temperatures too low for conventional carbon fusion. It's like trying to light a campfire with ice cubes, yet these stars are doing it effortlessly, churning out elements that defy every textbook model. The mystery deepens when we look at their chemical fingerprints. Spectroscopic analysis reveals traces of heavy elements like technetium and rubidium that shouldn't exist in these stars at all. These elements are so unstable, they decay rapidly unless constantly replenished. Even weirder, some of these materials are thought to form only in the unimaginable pressures of supernova explosions. Yet here they are, simmering quietly inside stars that haven't exploded. It's as if these stars have cracked a secret recipe for elemental cooking, one that bypasses the need for catastrophic stellar deaths. One theory points to slow neutron capture, a process where atoms gradually absorb neutrons over millennia, inching their way up the periodic table. But even this can't explain the sheer abundance of certain isotopes. Another idea suggests turbulent convection zones might be dredging up material from deeper, hotter layers, creating pockets where exotic fusion occurs sporadically. The wildest hypothesis, quantum tunneling on a stellar scale, where particles cheat their way through energy barriers that should be impenetrable. If true, it would mean stars can fuse elements at far lower energies than we thought possible, a revelation that could rewrite nuclear physics itself. Then there are the pulsators, stars that throb with rhythmic brightness changes, as if their cores are breathing unevenly. Some fluctuate with such precision they rival atomic clocks. Others sputter erratically, their pulses mismatched to their predicted nuclear output. These rhythms aren't just curiosities, they're direct windows into the star's internal furnaces. By studying their vibrations, astronomers have stumbled upon bizarre discrepancies. Certain pulsations imply core densities or temperatures that shouldn't exist alongside the star's surface composition. It's like hearing a symphony where the violins are playing in a different key than the brass section, a discord that hints at forces we've yet to name. What ties these anomalies together is their defiance of a fundamental assumption that stars are predictable nuclear reactors. Instead, they suggest a cosmos far more inventive, where elements might form through pathways we've never imagined. Some researchers speculate these stars could be tapping into dark matter particles, their collisions providing just enough extra energy to spark unusual fusion. Others wonder if magnetic fields are twisting plasma into knots where nuclear rules bend. Whatever the answer, one thing's clear: the periodic table's origin story is missing pages, and these stars hold the ink to fill them in. And if stars can forge elements in ways that baffle us, what happens when we find ones that refuse to fuse at all? Not every stellar oddity burns too creatively. Some seem to have forgotten how to burn entirely. The cosmos has its own heartbeat, a rhythmic pulse echoing through the void as stars expand and contract with clockwork precision. At least that's how it's supposed to work. But scattered across the galaxy are celestial mavericks whose rhythms defy the score, pulsating in erratic cadences that leave astronomers scrambling for explanations. These aren't minor tempo shifts, they're full-blown cosmic arrhythmias, stars throbbing in patterns that shouldn't exist based on their size, age, or composition. Take the case of KIC 8462852, a star so unusual it earned the nickname Boyagian star, after the astronomer who first documented its bizarre behavior. Most pulsating stars dim and brighten like a metronome, their cycles tied to internal pressure waves. But this star's light curves look like a seismograph during an earthquake, spikes and dips with no discernible pattern. Some dips last days, others vanish in hours. The strangest part, these fluctuations can't be explained by any known stellar process. Dust clouds, too irregular. Planetary debris, not nearly enough material. The leading theory, something massive and unseen, perhaps a shattered planet or a swarm of comet fragments, is passing in front of the star in a chaotic orbit, casting ever-changing shadows. But even that feels like a placeholder answer for a phenomenon we've yet to truly grasp. Then there are the heartbreak stars, binary systems where one star's pulsations mysteriously sync with its companion's orbit, as if locked in a gravitational tango we can't hear the music to. Normally, binary partners influence each other's rhythms predictably, like pendulums swinging in tandem. But in systems like Rs Canum Venaticorum, the pulses accelerate and decelerate at random, as if the stars are arguing over the tempo. The culprit might be magnetic war, fair sunspots and flares creating drag or turbulence between the pair. Or it could hint at something deeper, tidal forces distorting the star's cores in ways our models don't account for, warping their natural vibrations like fingers pressing on a guitar string. But the real head-scratchers are the silent pulsators, stars that should be throbbing wildly based on their internal structure, yet remain eerily still. Imagine a bell forged to ring at a specific pitch, only to discover it's utterly mute when struck. That's the enigma of HD 49309, a massive star whose core physics demand vigorous pulsations, yet its surface betrays no sign of them. One possibility, its core is stratified in unexpected ways, with layers of differing densities smothering the vibrations before they reach the surface. Another, more radical idea, exotic particles like Action's hypothetical dark matter candidates could be absorbing the energy, turning the star's heartbeat into a whisper. These anomalies aren't just academic curiosities. They're seismic disruptions to asteroseismology, the field that uses stellar vibrations to probe interiors like cosmic ultrasound. Every mismatched pulse implies gaps in our understanding of how energy moves through stars, how matter behaves under extreme pressures, or even how gravity operates in layered environments. And just when we think we've catalogued every possible stellar rhythm, the universe throws another curveball, stars spinning so fast they threaten to tear themselves apart. Which brings us to the speed demons of the cosmos, stars rotating at velocities that defy physics as we know them. Conventional wisdom says massive stars should slow down with age, like figure skaters extending their arms. But VFTS 102 in the Tarantula Nebula spins at over 600 kilometers per second, nearly fast enough to fling itself apart. At that velocity, centrifugal force stretches the star into an oblate spheroid, its equator bulging outward while its poles grow dangerously thin. The math suggests it should have shattered eons ago, yet it persists, a whirling dervish mocking the limits of stellar endurance. How do these stars cheat destruction? One theory points to magnetic brakes, fields so intense they act like cosmic seatbelts, holding the star together against its own momentum. Others speculate these speedsters might be stellar vampires, siphoning gas from a companion star to replenish their thinning outer layers. But the most intriguing possibility, they're the survivors of catastrophic mergers, their rotation turbocharged by the angular momentum of two stars colliding and combining. Whatever the truth, their existence proves that when it comes to stellar evolution, the universe still holds the wildest cards close to its chest. There's a point where spinning too fast stops being impressive and starts defying physics entirely, and that's exactly where these stellar speed demons live. Picture a star rotating so violently, its equator bulges outward, stretched thin like taffy, while centrifugal force tries to fling its outer layers into space. By all rights, these stars should disintegrate, their matter scattered across the void. Yet against every prediction, they hold themselves together, spinning at velocities that rewrite the rules of stellar survival. Take VFTS 102, a massive star in the Large Magellanic Cloud whirling at over 600 kilometers per second. At that speed, its surface gravity is barely winning the tug of war against its own rotation, creating a star that's more squashed sphere than perfect orb. So how do these cosmic tops keep from flying apart? One clue lies in their often turbulent origins. Many appear to be the products of stellar mergers, two stars colliding and combining their angular momentum into a single, dizzying whirl. Imagine two ice skaters clasping hands and spinning faster as they pull closer. Now scale that up to stellar proportions, with the resulting star inheriting a rotation rate that borders on suicidal. Others might owe their speed to vampiric tendencies, siphoning material and rotational energy from a binary companion. As gas spirals from one star to another, it transfers momentum, effectively revving up the recipient like a cosmic engine. But the real shocker, these stars don't just challenge stability, they broadcast their chaos across the universe. Some spin so rapidly, they warp space-time itself, emitting faint gravitational waves that ripple through the cosmos. These aren't the catastrophic waves produced by colliding black holes. They're subtler, a constant hum of distortion woven into the fabric of reality. Detecting them requires instruments of ludicrous sensitivity, yet their very existence proves that even a single star, spinning fast enough, can leave fingerprints on the universe's structure. What fascinates astronomers most isn't just the stars' defiance of physics, it's the aftermath of their rebellion. Many eventually shed their excess energy by launching colossal stellar winds, ejecting mass at speeds that paint surrounding nebulae with intricate spiral patterns. Others might collapse into pulsars, their rapid spins preserved in the dense remnants they leave behind. And then there are the outliers, stars like Vega, which rotates so fast its poles are significantly hotter than its equator, creating temperature imbalances that scramble our models of stellar atmospheres. Yet for all their violence, these whirling dervishes serve a crucial purpose. They're natural laboratories for extreme physics. By studying them, we probe the limits of hydrodynamics, plasma behavior, and even quantum effects under conditions impossible to replicate on Earth. Each one is a reminder that the universe doesn't just tolerate chaos, it thrives on it, crafting phenomena that stretch our understanding to the breaking point. And if stars spinning themselves ragged aren't strange enough, wait until you hear about the ones that show up where they absolutely don't belong, like intergalactic vagabonds drifting far beyond any galaxy's grasp, or ancient stars lurking in places too young to host them. The cosmos has a habit of dropping its celestial residents in the least expected corners, and the reasons will leave you questioning everything you thought you knew about stellar real estate. Stars don't just live in galaxies, some are cosmic hermits, drifting through the vast emptiness between galaxies like lone sailors on an endless ocean. These aren't just stars that wandered too far from home. They're celestial outcasts, isolated in regions so devoid of matter that their very existence defies our understanding of where and how stars can form. Picture a single star, untethered from any galactic structure, burning quietly in a void where the nearest neighbor might be millions of light years away. How did it get there, and what does its loneliness tell us about the hidden violence of the universe? One explanation points to galactic ejections, cataclysmic events where stars are flung out of their home galaxies at speeds too great for gravity to reclaim them. Imagine a binary star system venturing too close to a supermassive black hole. The black hole's immense gravity could capture one star while hurling its companion into the abyss like a slingshot projectile. These hypervelocity stars might eventually escape their galaxy entirely, condemned to drift forever in intergalactic space. But here's the catch: not all isolated stars move fast enough to support this theory. Some drift lazily as if they were born in the void itself, a notion that contradicts everything we know about star formation, which requires dense clouds of gas and dust. That's where the mystery deepens. Could there be pockets of star-forming material hiding in these so-called empty regions? Astronomers have discovered faint, diffuse clouds of hydrogen floating between galaxies, remnants of cosmic collisions or filaments from the universe's large-scale structure. Under the right conditions, these wisps of gas might collapse into stars, though the process would be far slower and rarer than in galaxies. Even more intriguing are the rogue planets and brown dwarfs found in similar isolation, hinting that whole populations of celestial orphans might exist, invisible to all but our most sensitive telescopes. Then there's the dark matter angle. Some theorists suggest these lonely stars could be tracers of dark matter, halos, invisible structures massive enough to gather gas and trigger star formation, yet too dim to detect directly. If true, each isolated star might be the tip of an unseen iceberg, marking the presence of dark matter clumps that refuse to reveal themselves any other way. Others propose even wilder ideas, like stars forming in the turbulent wakes of ancient quasars or ejected from galaxies during violent mergers billions of years ago. What makes these intergalactic wanderers so revolutionary isn't just their origin story, it's what they imply about the universe's past. Every solitary star is a fossil record of some forgotten cosmic upheaval, a relic of collisions, ejections, or formations we've yet to witness. They force us to reconsider how much of the universe's stellar population might exist outside galaxies entirely, hidden in the darkness between the lights. And if stars can form or survive in such extreme isolation, what else might be lurking in the voids, waiting to upend our cosmic senses? The universe, it seems, is far less tidy and far more inventive than we ever imagined. Stars wrapped in cosmic enigmas, these aren't the elegant, symmetrical nebulae we're used to seeing in textbooks. Instead, they're chaotic, twisted structures, as if the universe itself took a brush and painted outside the lines. Some resemble hourglasses with pinched wastes of glowing gas, while others spiral like galactic whirlpools or stretch into jagged, irregular shapes that defy simple classification. What's even stranger, the stars at their hearts often behave nothing like their placid cousins, emitting light and energy in patterns that make no sense under conventional astrophysics. Take the Red Rectangle Nebula, for instance, a cosmic geometry project gone wrong. Its nested ladder-like rungs of dust and gas glow an eerie crimson, a structure so precise it looks almost engineered. The culprit, a dying star at its core, pumping out twin jets of material in opposite directions while a dense disk of debris forces the outflow into this bizarre, angular shape. But here's the puzzle. The star's light shows unexpected spikes of ultraviolet radiation, as if something hidden, perhaps a companion star or a warped magnetic field, is superheating the nebula from within. Then there's the cosmic butterfly, a bipolar nebula with wings of gas stretching light years across. These lobes should be symmetrical, sculpted by steady stellar winds. Yet one wing flickers with violent turbulence while the other remains eerily calm, like a butterfly with one fluttering wing and one frozen in time. Astronomers suspect an unseen partner, a second star or even a black hole, might be disrupting the outflow, tugging at the nebula's structure like a puppeteer pulling invisible strings. But the real showstoppers are the nebulae that act like natural telescopes. A handful of these structures bend and magnify their central star's light so dramatically, they mimic the effects of gravitational lensing, a phenomenon usually caused by the warping of space-time around massive galaxies. Except these aren't galaxies. They're comparatively tiny stellar remnants, yet their intricate dust lanes and shockwaves distort light in ways that rival cosmic heavyweights. One theory suggests ultra-dense rings of material around the star could be responsible, acting like a funhouse mirror for photons. Another, more radical idea. These nebulae might harbor exotic matter particles with unusual refractive properties scattered like glitter in their gaseous veils. What binds these anomalies together isn't just their peculiar shapes, it's the light they emit. Many glow in spectral lines that shouldn't exist, their atoms excited by processes we've yet to decipher. Some pulse with infrared signatures indicating temperatures far hotter or colder than their stars should produce. Others flicker in X-rays without any obvious source, as if the nebulae themselves are generating energy through mechanisms we can't yet model. And just when you think it can't get any stranger, there's the case of nebulae that seem to be evolving. Unlike the static snapshots we expect from these cosmic clouds, a few change shape over mere decades. They're tendrils of gas retreating or surging outward at speeds that defy the gentle push of stellar winds. It's as if something inside them is alive, reshaping its surroundings with a mind of its own. Whether it's magnetic storms, hidden stellar companions, or something even more exotic, one thing's clear: these nebulae aren't just shrouds of dust and gas. They're cosmic laboratories, testing the limits of physics in ways we're only beginning to glimpse, which raises an even more tantalizing question. If nebulae can warp light and emit impossible radiation, what happens when we find stars that don't just bend the rules of physics, but rewrite them entirely? Stars don't just shine sometimes, they communicate. Or at least, that's what it looks like when we catch them emitting light signals that have no business coming from a stellar surface. These aren't the gentle flickers of variable stars or the predictable pulses of a pulsar. These are bursts of light in patterns so precise, they've made even the most skeptical astronomers pause. Take the infamous KIC 552888, a star whose light curves dip in a sequence that resembles Morse code more than astrophysics. For years, researchers scrambled to explain it: dust clouds, planetary debris, but none of the answers quite fit. Then there's VVVWIT-007, a giant that dims by 80% at irregular intervals, as if something colossal and shapeless is drifting in front of it. The unsettling truth: we still don't know what something is. What makes these signals so unnerving isn't just their strangeness, it's their specificity. Some repeat at intervals too regular to dismiss as chaos, like cosmic metronomes ticking against the void. Others flare in spectral lines that shouldn't exist, wavelengths corresponding to no known atomic transition. One hypothesis suggests ultra-dense plasma structures, twisted by magnetic fields into unnatural configurations, might be responsible. Imagine a star's atmosphere knotting itself into a temporary laser, amplifying light in ways we've never seen. Another theory points to quantum anomalies in the star's core, where extreme pressures might be triggering rare particle interactions that leak energy as bizarre photons. Then there's the elephant in the room, the SETI factor. When a star's light patterns resemble deliberate sequencing pulses spaced at prime numbers, say, it's hard not to wonder: could these be nature's version of a cosmic strobe light, or something else entirely? The debate rages, but here's the twist: even if the signals are natural, they're revealing gaps in our stellar physics. For instance, some of these stars emit far more ultraviolet or infrared light than their temperatures should allow, as if their surfaces are hotter or colder than the models permit. It's like opening an oven set to 300 degrees and finding one corner frozen solid while another blisters at 1,000. The real shocker: a handful of these stars don't just emit odd light, they absorb it peculiarly too. Their spectra show missing wavelengths, as if something inside them is siphoning energy at specific frequencies. One explanation involves exotic molecules forming in their atmospheres, structures so fragile they'd never survive Earth labs. Another, more radical idea: microscopic cosmic strings, hypothetical defects in spacetime, could be threading through these stars, warping the light that passes near them. So where does this leave us, staring at a cosmos that's either far more inventive than we guessed, or quietly hinting that we're not alone? Either way, these stars aren't just anomalies, they're invitations to rethink the boundaries of the possible. And if light itself can behave so unpredictably, what else might be hiding in plain sight, waiting for us to notice? Stars aren't supposed to break the laws of thermodynamics, yet here we are, staring at cosmic rebels that do exactly that. Imagine a star with a core burning at a blistering 15 million degrees, while its surface chills at a mere 3,000, like a campfire with flames hotter than the sun, but a warmth you could almost reach out and touch. These aren't just quirks of stellar anatomy, they're full-blown thermodynamic paradoxes, defying every model of how energy should move through a star. And the strangest part, the math says these gradients shouldn't exist. Heat always flows from hot to cold, smoothing out extremes unless something hidden is warping the rules. Take yellow supergiants like Rho Cassiopeae. These massive stars should have relatively uniform temperature distributions, their energy radiating outward in predictable waves. Yet spectroscopic readings reveal patches of their surfaces are hundreds of degrees cooler than their surroundings, as if someone flicked off sections of a stellar furnace. One theory points to convection gone rogue, massive plasma bubbles rising too slowly from the core, cooling abnormally before breaching the surface. But here's the catch. Simulations show these stars' interiors should mix too violently for such sluggish bubbles to form. Unless, of course, their magnetic fields are threading through the plasma like invisible barriers, corralling heat into strange, uneven patterns. Then there's the case of cold spots, localized regions on stars like Roman 20 Trianguli where temperatures plummet inexplicably. These aren't mere sunspots, they're vast, deep chill zones spanning thousands of kilometers, some persisting for decades. The leading explanation, stellar magnetism twisted into knots, creating areas where energy is trapped beneath the surface like steam under a locked lid. But even that doesn't fully explain the sheer scale of these anomalies. Some researchers speculate these stars might harbor internal energy sinks, structures or particles absorbing heat before it can reach the surface. Dark matter, if it interacts weakly with normal matter, could theoretically pool in a star's layers, acting as a cosmic sponge for thermal energy. Far-fetched. Perhaps, but when conventional physics falls short, the universe often demands unconventional answers. The real enigmas, though, are the stars that flip the script entirely, hot surfaces masking cooler cores. K-type giants like Epsilon Eridani exhibit this inverted logic, their outer layers blazing hotter than their internal models predict. It's as if these stars are wearing heated jackets over icy hearts. One tantalizing possibility involves acoustic waves, sound energy generated in the core and converted to heat as it travels outward, like ocean waves crashing into a cliff and spraying foam upward. Another theory suggests these stars might be polluted by ingested planets or asteroids, their heavy element-rich debris altering opacity in the outer layers and trapping heat unnaturally. What ties these anomalies together is their defiance of a fundamental truth. Stars should be thermal equilibriums, their energy flows smooth and predictable. Instead, they're cosmic mavericks, proving that even the most basic laws of physics have loopholes we've yet to uncover. And if thermodynamics can bend inside a star, what other, immutable rules might be more flexible than we think? Now imagine a star that not only breaks the rules of heat, but the rules of time itself. Some stars burn steadily for billions of years, then suddenly. Don't die, no supernova, no collapse into a white dwarf, just an endless twilight glowing faintly long after their fuel should have run out. These aren't just old stars, they're celestial vampires feeding on some hidden reservoir of youth we can't yet see. There's a cosmic irony to stars that refuse to die, celestial Methuselas burning defiantly long after their funeral pyres should have gone cold. These aren't just old stars clinging to life. They're cosmic anomalies that have exhausted their nuclear fuel yet somehow keep shining, like a flashlight with dead batteries that won't flicker out. Take the bizarre case of He 1057-2180. a white dwarf that's been glowing for billions of years, longer than its hydrogen reserves should allow. By all rights, it should be a cold, dark cinder by now. Instead, it pulses with a faint but steady light, as if drawing energy from some hidden well. One radical explanation: dark matter annihilation. If certain hypothetical particles like weakly interacting massive particles, or WIMP, exist, they could accumulate in a star's core over eons. There, they'd collide and annihilate, releasing energy that supplements the star's fading nuclear fires. It's like tossing logs into a dying campfire, except the logs are invisible and the fire burns on pure mystery. The math suggests this process could extend a star's life by billions of years, turning it into a kind of cosmic lantern fueled by the universe's shadowy side. Then there are the stellar zombie stars resurrected by violent encounters. Picture a white dwarf, cold and dark, drifting through the galactic graveyard until it collides with another remnant or siphons gas from a passing cloud. The impact or accretion could reignite fusion in its corpse, creating a temporary second life. But some of these reborn stars show no signs of recent collisions or cannibalism, leaving astronomers to wonder if other mechanisms like unstable phase transitions in their degenerate matter might be pumping fresh energy into their hearts. What makes these eternal stars so unsettling isn't just their defiance of timelines, it's what they imply about the universe's hidden energy budgets. If stars can tap into dark matter or revive themselves without obvious triggers, our models of stellar evolution are missing entire chapters. And if that's true, how many other dead stars might still be flickering in the darkness, unseen? Now, flip the script. While some stars cling to life past their expiration dates, others detonate far too soon like cosmic fireworks with faulty fuses. Massive stars are supposed to live fast and die young, but even by those standards, supernova precursors like SN 2005 HL explode with baffling haste. These aren't just premature deaths, they're stellar suicides with no clear trigger, collapsing into violent explosions long before their cores should have run out of fuel. One culprit might be pair instability, a runaway reaction where photons in the core spontaneously convert into electron-positron pairs, sapping the star's internal pressure until it implodes. But that process should only occur in stars of a very specific mass range, and yet we've spotted these early explosions in stars that don't fit the profile. Others might be victims of internal theft, where a hidden black hole or neutron star companion siphons away their mass, destabilizing them prematurely. The weirdest cases, stars that explode twice. Some supernova, like IPTF14 flare up, fade, and then erupt again months later, a phenomenon that defies the standard one and done model of stellar death. It's as if the star's core collapses in fits and starts, or something inside it is reigniting the blast wave like a stubborn match. Whether it's exotic physics or unseen stellar partners, one thing's clear: the universe has more ways to kill a star than we ever dreamed. And when it comes to cosmic lifespans, the rulebook is looking thinner by the minute. Massive stars are supposed to follow a predictable life cycle, burning bright for millions of years before ending in a spectacular supernova. But the universe has a habit of breaking its own rules, and some stars take their final bow far too early, detonating like cosmic alarm clocks set to the wrong time. These aren't just statistical outliers, they're full-blown anomalies, exploding with such untimely violence that they force us to question whether we've misunderstood stellar death entirely. Take the case of SN 2012Z, a supernova that erupted in a star barely past its adolescence, a cosmic teenager that should have had eons of fuel left to burn. Instead, it tore itself apart with the fury of a star 3 times its age, leaving astronomers scrambling for explanations. What could cause a star to self-destruct prematurely? One possibility lies in hidden instabilities buried deep within their cores. Normally, stars balance the crushing force of gravity with the outward pressure of nuclear fusion, maintaining a delicate equilibrium. But some massive stars might harbor unseen flaws, regions where energy transport goes haywire, or where exotic particles warp the rules of thermodynamics. Picture a champagne bottle shaken too hard. Even if the glass looks intact, the pressure inside can trigger an explosion at the slightest weakness. Similarly, these stars could be ticking bombs, their cores teetering on the edge of collapse long before their fuel runs dry. Then there's the wild card of external triggers. Imagine a star cruising through a dense molecular cloud or grazing the gravitational field of a nearby black hole. The added stress could compress its core just enough to tip it over the edge, like a boulder dislodged by a single gust of wind. Some researchers even speculate about stellar collisions, two stars merging in a cataclysm so violent it bypasses the usual death sequence entirely. But the strangest cases are the supernovae that leave behind remnants defying all expectations. Instead of a neutron star or black hole, some explosions produce bizarre, hollow shells of gas or objects with densities that don't match any known stellar corpse. It's as if these stars didn't just die early, they died wrong, leaving behind relics that shouldn't exist. The implications are staggering. If stars can explode prematurely, our supernova classification system, built on the assumption of predictable lifespans, might need a complete overhaul. Worse yet, these anomalies hint at gaps in our understanding of core physics. Are there unknown particles influencing stellar stability? Could dark matter be pooling in these stars, hastening their demise? Every unexpected explosion is a clue, a cosmic breadcrumb pointing toward forces we've yet to name. And just when you think stellar death couldn't get any stranger, the universe throws us the ultimate curveball, stars that refuse to die at all. While some detonate too soon, others cling to life with unnatural tenacity, burning on despite every law that says they shouldn't. Some stars don't just cheat death, they mock it outright, burning defiantly long after their cores should have collapsed into oblivion. These aren't just old stars clinging to life, they're cosmic anomalies that rewrite the rules of stellar mortality. Take V Hydrae, a carbon star that's been hemorrhaging mass for centuries, ejecting vast plumes of gas in violent bursts. By all accounts, it should have exhausted itself long ago, yet it persists, flickering erratically as if fueled by some hidden reservoir of energy. The mystery deepens when we examine its structure. Most dying stars shed material in smooth, predictable outflows, like smoke rising from a candle. But V Hydrae's ejections are chaotic great gouts of gas launched in opposing directions at uneven intervals, as if something inside is stirring the pot. One theory suggests an invisible companion, perhaps a white dwarf or neutron star, could be orbiting close enough to disrupt the dying star's death throes, siphoning its material and occasionally reigniting fusion in its core. Another, more radical idea: the star's core might be transitioning into an exotic state of matter, where quarks or other particles rearrange themselves in ways that release unexpected bursts of energy. Then there's the case of Mera variable stars that pulse rhythmically as they near the end of their lives, growing brighter and dimmer like cosmic lighthouse beacons. Most fade into obscurity after a few thousand cycles, but a handful, like our Hydrae, suddenly rejuvenate, their pulsations stabilizing as if they've tapped into a second wind. Spectroscopic analysis reveals traces of lithium in their atmospheres, an element usually destroyed in stellar cores. Its presence hints at fresh nuclear reactions occurring in layers that should have gone dormant, like embers flaring back to life in a dying fire. The real enigmas, though, are the stars that refuse to follow the script entirely. Luminous blue variables like Eta Carinae should have self-destructed in supernova explosions centuries ago. Instead, they undergo bizarre super outbursts, ejecting massive shells of material while their cores remain intact. It's as if these stars are testing the limits of their own mortality, teetering on the edge of collapse without ever quite tipping over. Some astronomers speculate their immense magnetic fields act like cosmic corsets, holding them together despite their violent convulsions. Others wonder if they're drawing energy from nearby sources, accreting material from unseen companions, or even tapping into the fabric of spacetime itself. What binds these cosmic survivors together is their defiance of time. They challenge the very definition of a star's lifespan, proving that death in the universe isn't always a one-way street. Some might be stealing energy from neighbors, while others could harbor internal engines we've yet to discover. But one thing's certain: their existence forces us to reconsider how stars live, die, and sometimes against all odds, refuse to do either. Now shift your gaze to the stars that don't just defy death, they defy gravity itself, tracing orbits so bizarre they rewrite the rules of celestial mechanics. These aren't just eccentric paths, they're cosmic roller coasters looping around voids, darting between galaxies, or even spiraling toward destinations that shouldn't exist. If the universe has a sense of humor, it's hiding it in the trajectories of these stellar rebels. Stars don't always follow the cosmic rulebook. Some carve paths so bizarre, they make astronomers question whether gravity itself has gone rogue. Picture a star racing backward around a galactic center, defying the orderly flow of its stellar siblings, or one tracing a steep, lopsided orbit like a drunkard stumbling through a crowded room. These aren't just celestial oddities, they're gravitational rebels, their trajectories scribbling question marks across our models of how galaxies work. Take hypervelocity stars, for instance, those ejected from galactic cores at breakneck speeds. While most flee in predictable arcs, a handful loop back in sharp, hairpin turns, as if some unseen hand yanked them off course. Others, like the so-called backward stars, orbit in perfect retrograde, moving opposite to their galaxy's rotation like salmon swimming upstream, the leading explanation. A violent past, perhaps a close encounter with a supermassive black hole that slingshotted them into chaos, or a catastrophic collision with another star that sent them careening off script. But here's the twist: some of these mavericks orbit regions lacking the gravitational heavyweights needed to explain their paths. That means either our black hole census is woefully incomplete, or something else, dark matter clumps, rogue planets with absurd mass, or even primordial defects in spacetime, is warping their trajectories. Then there are the stars tracing cryptic spirals or figure eights around galactic centers, patterns so precise they resemble celestial choreography. These orbits aren't just artistic flourishes, they're cosmic breadcrumbs pointing to hidden mass. Imagine a star circling an empty patch of space as if tethered to an invisible anchor. One theory suggests dark matter substructure, lumps of unseen material distorting spacetime like hidden reefs redirecting ocean currents. Another posits the gravitational echoes of ancient mergers, where long-dead galaxies left behind ghostly imprints that still tug on stars today. But the real head-scratchers are the stars that vanish mid-orbit, only to reappear years later tracing an entirely new path. It's as if they've slipped through a cosmic backdoor, bypassing the gravitational rules that should govern their movement. Could they be interacting with wormholes or other exotic spacetime shortcuts? Probably not. But their erratic journeys force us to confront just how much of the universe's mass might be hiding in plain sight, twisting the paths of stars into puzzles we're only beginning to decode. Now shift your gaze from rebellious orbits to an even stranger phenomenon. Stars that don't just move unpredictably, they blink out of existence entirely, leaving astronomers staring at empty sky where a star once blazed. These vanishing acts aren't mere flickers or camera glitches. They're full-blown cosmic disappearing tricks, with stars winking out overnight as if swallowed by the void. Stars that rise from the cosmic grave, these aren't just variable stars dimming and brightening on schedule. These are celestial phoenixes, fading to near invisibility over decades before roaring back to life with no warning, as if the universe hit a cosmic reset button. Take T Coronii Borealis, a star that's pulled this vanishing act at least twice in recorded history, once in 1866 and again in 1946, each time dropping from naked eye visibility to the brink of telescopic detection, only to flare up hundreds of times brighter months later. It's not just defying expectations, it's rewriting the playbook on stellar death and rebirth. What could possibly fuel these resurrection cycles? The leading theory points to binary systems where a white dwarf siphons material from a bloated companion. As stolen gas accumulates on the dwarf's surface, pressure builds until it triggers a runaway thermonuclear explosion, a nova. But here's the catch: some phoenix stars brighten without the telltale signatures of nova eruptions, and their recovery times don't match the math. V Sagittae, for instance, has been brightening steadily for over a century with no explosive spikes, as if it's being slowly revived by some unseen Roman IV drip of stellar energy. Even stranger are the solitary phoenix stars, no binary partners in sight. Their recoveries suggest internal processes we've never witnessed, like dormant fusion zones reigniting deep within their cores. Imagine a campfire where embers smolder unseen for years before suddenly catching a gust of wind. Some researchers speculate these stars might be hoarding reservoirs of heavy elements that alter their opacity, trapping heat until it bursts free in unpredictable flares. Others wonder if they're victims of cosmic heists, having their outer layers stolen by invisible black holes or neutron stars, only to rebuild themselves over millennia. Then there's the timescale problem. Most variable stars operate on reliable schedules, weeks, months, maybe a few years between cycles, but phoenix stars laugh at timetables. Some vanish for centuries before returning, like U Scorpii, which erupts roughly once a decade, while others, like V605 Aquila, take millennia between performances. It's as if these stars are playing by rules written in a language we haven't deciphered yet. The most unsettling cases are the ones that don't just brighten, they transform. V838 Monocerotis didn't just flare in 2002. It ejected concentric shells of dust that glowed like cosmic tree rings, revealing layers of its history we'd never have seen otherwise. Was this a stellar merger, a dying gasp, or something entirely new? Decades later, we still don't know. And that's the heart of the mystery. Every phoenix star seems to operate on its own peculiar logic, forcing us to question whether stellar evolution is even the right term for whatever it is they're doing. Now shift your focus from stars that cheat death to ones that break the rules of companionship, because when it comes to cosmic relationships, some stars don't just defy expectations, they shatter them entirely. There's something deeply unsettling about a cosmic odd couple, a star locked in orbit with something that shouldn't exist beside it. Picture a fiery young giant twirling gracefully around a pitch-black void, or a fragile red dwarf shackled to a dense, spinning neutron star. These aren't just mismatched pairs, they're gravitational paradoxes, duos so improbable they make astronomers question whether we've misunderstood how stellar relationships form. Take the case of LB1, a massive blue star dancing with a black hole nearly 70 times heavier than our Sun. By all rights, a black hole that size shouldn't exist in our galaxy supernova models, say stars that massive should obliterate themselves entirely, leaving nothing behind. Yet there it is, silently tugging at its luminous partner as if taunting our theories. Then there's the mystery of red dwarfs with neutron star companions. These tiny, cool stars are the cosmic equivalent of houseplanets, dim, stable, and utterly unremarkable. So how did one end up paired with a city-sized stellar corpse packing the mass of a sun? Neutron stars are born in violent supernova, explosions so powerful they should have vaporized any nearby low-mass stars or at least kicked them loose. Yet systems like J1311-3430 exist, with a pulsar whirling so close to its red dwarf partner that their orbital period is just 93 minutes. The pulsar's radiation is slowly evaporating the dwarf, leaving a glittering trail of ionized gas like cosmic breadcrumbs. Did they form together against all odds, or was this a gravitational kidnapping? But the real head-scratchers are the systems where one partner defies classification entirely. In 2020, astronomers spotted a star orbiting something. Not a black hole, not a neutron star, but an object roughly 2.6 solar masses, a weight that lands it squarely in the mass gap between the heaviest neutron stars and the lightest black holes. It emits no light, no radio pulses, just a gravitational tug. Is it a bloated neutron star swollen with exotic matter, a featherweight black hole born from a rare, fizzled supernova? Or something entirely new, a celestial body we haven't even named yet? These mismatched pairs do more than puzzle us, they expose glaring holes in our understanding of binary formation. Conventional models say stars in pairs should be siblings, born from the same gas cloud with proportional masses. But these outliers suggest a cosmic undercurrent of violence, stellar theft, chance gravitational captures, or mergers that warp the rules. Some might be survivors of triple systems where one star was ejected or consumed, leaving behind an unlikely duo. Others could be the products of runaway stars, flung into chaotic orbits by past supernova or close encounters with other giants. And then there's the ultimate cosmic irony, stars that somehow shine alongside partners that should have snuffed them out. White dwarfs stealing matter from red giants often trigger nova explosions, yet a handful of these systems burn steadily, as if the dwarf is feeding gently enough to avoid catastrophe. How perhaps magnetic fields are regulating the flow, or the stolen gas is spiraling in at just the right angle to prevent a thermonuclear tantrum. Whatever the reason, these couples are walking a razor's edge, proof that even in the violent cosmos, there are partnerships that defy the odds, bending the rules without breaking them. Which makes you wonder, if stars can thrive alongside impossible companions, what other cosmic exceptions are we missing? The universe, it seems, has a flair for the dramatic, pairing its inhabitants in ways that keep us forever guessing. Dark stars sound like something ripped from a fantasy novel, celestial giants glowing not from nuclear fusion, but from the annihilation of dark matter itself. These hypothetical monsters could rewrite the rules of stellar physics, bridging the gap between the visible universe and its shadowy counterpart. Imagine a star 1,000 times wider than our sun, its core packed with weakly interacting massive particles, WIMP, colliding and releasing energy as gamma rays. No hydrogen, no helium, just pure dark matter burning like an invisible furnace. While we've yet to confirm their existence, a handful of bizarre objects in deep space radiate energy signatures that eerily match these predictions, leaving astronomers wondering if we're on the verge of a cosmic paradigm shift. Take the enigma of He0107-5240, a star so massive and bright, its energy output defies conventional models. spectroscopic analysis reveals no traces of heavy elements typically forged in stellar cores, as if its light comes from something else. Then there's J0315-1906, a distant giant emitting unexplained X-ray flares that align with theoretical dark matter annihilation profiles. Could these be the smoking guns of dark stars, or just cosmic red herrings? The answer might lie in their surroundings. True dark stars would likely form in dense dark matter halos, regions where invisible particles cluster like unseen mountains distorting the gravitational landscape. If we find stars shining anomalously bright in these zones, the case strengthens. The implications are staggering. Confirming a dark star wouldn't just add a new class of celestial object, it would prove dark matter can clump, interact, and power cosmic structures in ways we've never witnessed. These stars could be relics of the early universe, formed before normal matter dominated, flickering like ghostly candles in the cosmic dark. And if they exist, their remnants might still lurk today, collapsed dark matter cores masquerading as black holes, or even stranger objects we've yet to imagine. Now shift your gaze from the invisible to the unimaginably dense. Stars so massive, they don't just bend space-time, they twist it into knots. Picture a stellar behemoth where gravity wins its eternal war with light, warping the very fabric of reality around it. These aren't just heavy stars, they're cosmic funhouse mirrors, distorting everything from starlight to time itself. Take the bizarre case of LB1, a star orbiting what appears to be a black hole of impossible size. But what if the companion isn't a black hole at all? Some theorists suggest it could be a gravastar, a hypothetical object with an exterior of ultra-dense matter and a core of nothing. A true vacuum stabilized by dark energy, its surface bending light so severely it mimics a black hole's event horizon. The key difference: gravastars might not have singularities, offering a loophole in Einstein's equations where spacetime doesn't tear, it rebounds like a rubber sheet stretched to its limit. Then there's the even wilder possibility of Planck stars, stellar remnants so compressed they reach the Planck density where quantum gravity takes over. These objects might appear as black holes from afar, but their cores could be bubbles of spacetime frozen at the moment of collapse, like a cosmic paused film. If they exist, light escaping their edges could carry imprints of the universe's most extreme physics, a message in a bottle from the edge of reality. The real test lies in the details. True spacetime warping stars would leave fingerprints in the light they distort, subtle spectral shifts or polarization patterns unlike anything produced by black holes. Future telescopes like the Laser Interferometer Space Antenna might detect the gravitational waves they emit, revealing whether these objects are cosmic mirages or the universe's most brilliant sleight of hand. Either way, they remind us the cosmos doesn't just play by the rules, it rewrites them in the margins where gravity and quantum mechanics collide. Some stars don't just pull on spacetime, they twist it into knots, warping the fabric of reality in ways that defy every equation in the book. These aren't your average celestial heavyweights, they're cosmic anomalies where gravity behaves like it's been dialed up to 11. Bending light into eerie rings and distorting the orbits of nearby objects as if invisible hands are tugging at them. Take the curious case of KIC 8462852, a star whose gravity appears to flex and ripple unpredictably, lensing background starlight into patterns that suggest hidden mass or something far stranger. One explanation points to exotic matter lurking within these stars, particles that interact with gravity differently than ordinary atoms. Picture a star's core packed with hypothetical, strange quark matter, a dense, ultra-stable form of material that cranks up gravitational pull without adding detectable mass. It's like stuffing a neutron star's worth of density into a sun-sized package, creating a gravity well that shouldn't exist. Then there's the dimension-bending theory. If extra-spatial dimensions exist beyond the three we experience, certain stars might be leaking gravity into these unseen layers, amplifying their effects in our observable universe. Imagine a water stain seeping through wallpaper. What we perceive as anomalous gravity could be the cosmic equivalent of a hidden dimension's shadow. But the real showstoppers are the stars that lens light asymmetrically, as if space-time around them is crumpled like a piece of paper. Normally, gravitational lensing creates smooth arcs or Einstein rings, symmetrical halos of distorted light. Yet around stars like HD 106906, the lensing effect is jagged and uneven, like a funhouse mirror shattered and hastily glued back together. Some researchers speculate these stars might be orbited by invisible, ultra-dense objects, primordial black holes or quark nuggets, left over from the Big Bang, warping space-time in their vicinity. Others wonder if we're seeing the fingerprints of gravastars, hypothetical objects with vacuum cores that repel gravity at their surfaces, creating bizarre lensing artifacts. What ties these anomalies together is their defiance of Einstein's tidy equations. They're not just challenging our models, they're offering glimpses into physics that might lie beyond relativity, where gravity, dark matter, and quantum mechanics collide in ways we've yet to map. And if stars can warp space-time this unpredictably, what other cosmic secrets might be hiding in their gravitational ripples? Now, shift your gaze from bent starlight to stars that don't just distort space, they bombard the cosmos with particles that shouldn't exist. These aren't your typical neutrinos or cosmic rays. They're enigmatic emissions that crackle with energy beyond what any known stellar process should produce. Picture a star firing off bursts of high-energy positrons or spitting out WIMP-like particles that leave no trace except a faint, ghostly shudder in detectors. These cosmic accelerators might be the universe's way of hinting at forces we've yet to name, or even dimensions we've yet to see. Stars aren't just celestial light bulbs, some double as nature's most powerful particle accelerators, firing off subatomic bullets with energies that dwarf anything we can produce on Earth. These cosmic railguns don't follow the standard playbook. Their magnetic fields twist into monstrous coils, launching protons and electrons at near-light speeds with forces that leave physicists stunned. Take the bizarre case of Eta Carinii, a hypergiant whose eruptions don't just blast gas into space, they generate gamma-ray flares so intense they've been detected over 7,000 light-years away. This isn't just a star throwing a tantrum. It's a natural supercollider, bending the rules of electromagnetism to hurl particles with energies reaching hundreds of tera-electronvolts. What makes these stellar accelerators so perplexing isn't just their power, it's their precision. Unlike the chaotic fury of supernovae, these particles emerge in focused jets or rhythmic bursts, as if guided by some invisible cosmic circuitry. Some researchers point to magnetic reconnection, a process where twisted field lines snap and realign, releasing energy like a rubber band stretched to its breaking point. But here's the catch: the energies observed exceed what even this violent process should produce. Could these stars harbor magnetic knots 1,000 times stronger than our models predict? Or are they tapping into quantum effects we've yet to observe, where particles gain energy by surfing space-time ripples near their turbulent surfaces? Then there's the cosmic ray connection. For decades, astronomers have traced ultra-high-energy cosmic rays particles packing the punch of a fastball crammed into a single proton, back to regions housing these anomalous stars. Yet when they look closer, the math doesn't add up. The particles arrive with signatures suggesting they've been accelerated multiple times, as if bouncing between invisible cosmic mirrors before reaching us. One radical theory suggests these stars might be entangled in vast magnetic webs, their fields interconnecting with neighboring stellar remnants to form a galaxy-wide accelerator network. Imagine a pinball machine where the ball keeps scoring without ever slowing down, except the ball is a proton and the machine spans light years. But the real curveball comes when these stars start changing their spots, literally. Spectroscopic studies reveal some particle-spewing stars are also cosmic alchemists, their surfaces inexplicably gaining or losing heavy elements over mere decades. Normally, stellar composition changes over millions of years as fusion alters their cores. But stars like Przybylski's star, a peculiar object laced with rare actinides like promethium and einsteinium, defy this logic. These elements decay so rapidly, their presence suggests ongoing nuclear processes we've never witnessed. Are the star's particle beams somehow transmuting surface material? Or could these be the fingerprints of alien physics, exotic states of matter where protons and neutrons rearrange themselves into isotopes that shouldn't exist in nature? The implications ripple far beyond astrophysics. If stars can synthesize super-heavy elements casually, it could rewrite our understanding of nucleosynthesis, the cosmic recipe that builds everything from carbon to gold. Even more tantalizing, some of these stars emit neutrino bursts with energy patterns that don't match any known nuclear reaction. Could they be producing particles beyond the standard model, offering clues to dark matter or hidden dimensions? Every anomalous pulse, every rogue particle, is a breadcrumb leading toward an unsettling truth. The universe's building blocks might be far stranger and far more dynamic than our periodic table suggests. Now consider the ultimate twist: stars that don't just accelerate particles, they seem to filter them. A handful of these stellar mavericks emit particle beams suspiciously devoid of certain energies, as if something inside is sieving subatomic debris with cosmic precision. It's as though these stars aren't just natural phenomena, they're laboratories running experiments we're only beginning to decode. And if that's true, what other cosmic secrets might they be hiding in their furious, flickering hearts? Stars are supposed to be the universe's most reliable alchemists, slowly fusing elements in their cores and mixing them outward over millennia, their chemical signatures remaining as steady as a heartbeat. But scattered across the cosmos are celestial shape-shifters, stars that rewrite their own chemical blueprints right before our eyes. These aren't subtle changes, they're full-blown stellar makeovers, with elements appearing and vanishing like cosmic sleight of hand. Take Przybylski's star, a bizarre object that seems to be conjuring rare earth metals out of thin air. Spectroscopic readings show promethium, an element so unstable it decays within years, somehow persisting in its atmosphere, alongside other heavy actinides that shouldn't exist in a star this old. It's like finding a candle that burns but never melts, defying every law of stellar chemistry. What could possibly fuel these transformations? One theory points to subsurface nuclear explosions, violent bursts beneath the star's surface where pockets of material ignite like buried dynamite, dredging up freshly forged elements. Picture a stellar version of underwater volcanoes, their eruptions punching through layers of gas to deliver exotic cargo to the surface. Another possibility involves stellar vampirism, where a hidden neutron star companion bombards its neighbor with high-energy particles, transmuting surface atoms into heavier isotopes through relentless nuclear bombardment. But the wildest hypothesis, quantum tunneling on a grand scale, where particles cheat their way through energy barriers that should block certain fusion pathways, allowing stars to cook up elements at temperatures far cooler than physics textbooks allow. Then there are the stars losing elements as fast as others gain them. Kappa Cancri, a bright giant in the Cancer constellation, has been shedding iron and titanium from its outer layers at rates that leave astronomers baffled. Normally, heavy elements sink toward a star's core over time, but this star appears to be ejecting them into space like a cosmic sprinkler. Some researchers speculate its magnetic field has twisted into a colossal funnel, channeling material away in a stellar wind laced with metal. Others wonder if it's recently ingested a metal-rich planet or asteroid, and the indigestion is causing it to violently expel the foreign material. What makes these chemical chameleons revolutionary isn't just their odd behavior, it's what they imply about the universality of stellar models. If stars can rewrite their compositions this dramatically, our entire understanding of galactic chemical evolution might need recalibrating. These anomalies could be the missing link explaining why some star clusters show unexpected element distributions, or why certain exoplanets harbor atmospheres with perplexing chemical cocktails. They force us to confront an uncomfortable truth. Stars might not be the predictable reactors we thought. Some could be cosmic cauldrons, stirring elements in ways we've yet to imagine, while others might be thieves or hoarders, selectively gathering or discarding materials based on rules we haven't deciphered. And just when you think stellar chemistry couldn't get any stranger, the cosmos unveils its ultimate wildcard stars that don't just change their makeup, but appear to be older than the universe itself. These celestial Methuselas don't just bend the rules of physics, they snap them in half, leaving us to piece together a cosmic puzzle where the edges don't fit. Deep in the heart of our galaxy, a stellar family portrait hangs crooked, a cosmic puzzle where the children appear older than their parents. This is NGC 6791, a star cluster that shouldn't exist, where suns with nearly identical chemical compositions span age gaps of billions of years. Picture a group of siblings where some are toddlers and others are senior citizens, all claiming to be born from the same event. Normally, star clusters are stellar nurseries where stars form together from the same gas cloud, aging in lockstep like classmates graduating the same year. But here, spectroscopy reveals stars with youthfully rapid spins alongside ancient, sluggish giants, all sharing the same elemental DNA. It's as if the universe somehow pressed pause and play on star formation within the same cradle, leaving astronomers grasping for explanations. The first clue to this conundrum lies in their chemical fingerprints. Stars born from the same molecular cloud carry matching traces of heavy elements like iron and magnesium, cosmic birth certificates proving their shared origin. NGC 6791 stars have these matching signatures, yet their ages measured by rotation rates, brightness, and nuclear fuel consumption range from sprightly 2 billion-year-olds to weary 12 billion-year-old relics. Current models say this spread is impossible. Gas clouds either collapse entirely into stars or dissipate, not linger for eons between bursts of activity. One radical theory suggests the cluster might have birthed multiple generations by cannibalizing passing gas streams, like a stellar spider catching fresh material in its gravitational web. Imagine a star-forming region that didn't fade after its first brood but lay dormant until new gas wandered too close, triggering a second, much later round of stellar births. But the plot thickens when we examine their orbits. These stars aren't just mismatched in age, they move together through the galaxy as a cohesive unit, ruling out the idea that younger interlopers accidentally joined an older group. Their shared motion implies they've been bound since formation, a family that somehow expanded across cosmic eras. Some astronomers speculate the cluster could be the remnant of a dwarf galaxy merger. Its original gas reservoir stretched and twisted during the collision, creating pockets where star formation reignited sporadically. Others propose a more unsettling idea, that certain regions within the cluster harbor conditions where time itself flows differently, perhaps due to dense dark matter halos warping spacetime locally. The implications ripple far beyond this one cluster. If stars can form in staggered generations within the same structure, entire chapters of galactic archaeology need rewriting. Suddenly, oddball stars peppering the Milky Way's halo, previously assumed to be lone wanderers, might be survivors of similar, impossible clusters that dispersed over time. Even more tantalizing, this could hint at unknown physics governing star formation, where gas clouds behave less like monolithic nurseries and more like cosmic crockpots, simmering intermittently across epochs. What makes NGC 6791 truly revolutionary isn't just its defiance of models, it's the way it blurs the line between star clusters and galaxies. Dwarf galaxies like the Large Magellanic Cloud show episodic star formation, but they're vast structures with complex dynamics. For a modest cluster to replicate this behavior suggests a middle ground we never knew existed, a missing link in how cosmic structures organize matter. Future telescopes like the Vera Rubin Observatory might uncover more of these chronological rebels, revealing whether they're cosmic flukes or the first glimpses of a universal process we've overlooked. Stepping back, these 23 anomalies aren't just celestial curiosities, they're cracks in the foundation of astrophysics, each one prying open doors to new realms of understanding. From stars that vanish without a trace to clusters that laugh at time, they remind us that the universe is far stranger, far more inventive than our textbooks dared suggest. Every oddity is a breadcrumb leading toward discoveries that could reshape not just how we see the cosmos, but our place within it, the greatest lesson. However much we think we know, the sky still holds mysteries that humble, thrill, and beckon us to look deeper. These 23 galactic anomalies aren't just cosmic oddities. They're glaring neon signs pointing to the gaps in our understanding of the universe. Every runaway star, every flickering giant, every ancient relic defying the age of the cosmos chips away at the tidy models we've built, revealing a reality far wilder than our textbooks ever imagined. Think about it, we've mapped the life cycles of stars with equations and simulations, only to find celestial rebels that break every rule, as if the universe itself is laughing at our attempts to pin it down. Take hypervelocity stars racing through the void like cosmic outlaws, proof that gravity's grip isn't as unshakable as we thought. Or Methuselah, the star older than time, whispering that our cosmic clock might be missing gears. Even the vanished stars, disappearing without supernova or black holes, hint at death mechanisms we've yet to witness. These aren't just quirks, they're clues, each one a breadcrumb leading toward discoveries that could rewrite astrophysics. And the most thrilling part, this is just the beginning. Every anomaly we've catalogued is a doorway to questions we haven't even thought to ask. Could dark stars, hypothetical giants fueled by annihilating dark matter, be lurking in the shadows? Are gravitational anomalies bending starlight in ways we've misread? The universe isn't just hiding secrets, it's daring us to look closer, to question deeper. What's truly humbling is realizing how much we don't know. For every mystery solved, like the pulsar timing anomalies once blamed on alien megastructures, now traced to interstellar plasma, dozens more emerge, each stranger than the last. It's a reminder that science isn't about having all the answers. It's about chasing the next question with curiosity and grit. So here's the challenge. The next cosmic rebel might be hiding in plain sight, waiting for an amateur astronomer's keen eye or a fresh dataset from the next generation of telescopes. Whether it's a star flickering in an impossible rhythm or a nebula warping light in ways Einstein wouldn't recognize, the universe is far from done surprising us. Keep watching the skies because the greatest discoveries aren't just about what we've found. They're about what we've yet to imagine.